What's up, Algebra Bros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear! Hey, today we're taking a look at section 1.4, talking about the matrix equation AX equals B. So let's go ahead and jump into it. So we'll start with the definition. We say if A is an m by n matrix with columns a sub 1, a sub 2, so on and so forth with a sub n. And here we're just defining what those columns look like to the matrix. So a sub 1 is the first column, a sub 2 is the second column, so on and so forth. A sub n is the nth column. And if a vector x is also in vector space Rn, so with n entries, then the product of a and x, denoted by ax, is the linear combination of the columns of A using the corresponding entries in X as weights. That is, A times X, written as AX. And here we can see we have this sort of written out longhand. So this is our matrix A, and here's the first column, A sub 1, second column, A sub 2, so on and so forth to A sub n is the nth column. Here's my vector X with these n entries in it. And we'll take the first entry, multiply it by this first column. We're going to add to it. We take the second entry, x2, multiply it by the second column, a sub 2, plus so on and so forth, until we get to the end. The last addend there is going to be the last entry of this vector, x sub n, times the column a sub n. And we'll say, well, notice here, this imposes a restriction. A times x is only defined if the number of columns in the matrix A, the number of columns I have here, is the same as the number of entries in this vector x. And then we have a nice theorem to follow this up with. We say if A is an m by n matrix with the columns a sub 1, a sub 2, so on and so forth to a sub n, and if B is a vector in Rn, then the matrix equation AX equals B has the same solution as the vector equation, and it's that same x sub 1 times a sub 1 plus x sub 2 times a sub 2 plus so on and so forth plus x sub n times a sub n as before, but now equals that vector B, which would really be the same as solving the system with the linear equations with the augmented matrix. Here I take the matrix with columns a sub 1 through a sub n, think of that like a coefficient matrix. I augment it with this vector B. And we'd say, okay, so if I solve that matrix equation, it's really the same idea. Well, let's talk about the existence of solutions. We say the equation AX equals B has a solution if and only if B is a linear combination of the columns of A. And we'll get a chance to talk about things like column space later on in the course, but we're saying, okay, so there has to be some solution here. It has to be a consistent system. And we're also going to talk about the row vector rule for computing A times X. Say if the product A times X is defined, then the ith entry in A times X is the sum of the products of the corresponding entries from row I of A and from the vector X. And then just a theorem to take a look at really quick before we jump into some problems. We have if A is an m by n matrix, and u and v are vectors in vector space Rn, and c is a scalar, just some real number, then we get the following property. So here I have matrix A times, in parentheses, vectors u plus v, so u and v being added. Here I have a nice distributive property. I can multiply in the matrix from the left, so I get A times u plus A times v. And then here dealing with scalar c, if I have matrix A times, and here in parentheses I have the scalar c times the vector u. If I'd like to, I could bring that scalar c all the way out in front, and I could focus on A times u first, and then I can worry about multiplying that scalar c in later. So I get that nice property. But let's go ahead and talk about, really sort of building some ideas, connecting matrices and vectors. I want to find the following products using the definition from above, working with the vectors as corresponding weights of columns, and then also using the row vector rule for computing. So we're actually going to be finding the product here in two ways. So think of this like A times X. Now the first way, the definition from above says what I want to do is, and here I can go ahead and label these, say this is matrix A times vector X. What I want to do is I want to take the entries in the vector X and use them as scalar weights on the corresponding columns of matrix A. So I'll take this first entry of X, which is -2, and I'm going to multiply that to the first column of A, which has entries 1, -3, 1. And then I'm going to add to this. Now I'm going to take the second entry of vector x, which is this 3 here, and I want to multiply that to the second column of matrix A, which had entries 2, 1, 6. Now I can just go through the arithmetic. Since we talked about how to do arithmetic with vectors previously, we can go ahead and do this now. If I multiply the -2 into every entry of this vector, we'll say, well, how is that going to look? Well, I'm going to get -2, then -2 times -3 gives me +6, then I get -2, and then I can add to this. Now if I multiply 3 into everything in this vector, 3 times 2 gives me 6, 3 times 1 is 3, 3 times 6 is 18. And then I can go ahead and add corresponding entries. So remember, if I'm going to add two vectors together of the same size, I want to add corresponding entries. So -2 plus 6 gives me 4. 6 plus 3 gives me 9. And -2 plus 18 gives me 16. So there we have the result, the answer. But this said to do this in two different ways. So the other way that I would do this, and I think this is really nice, it really shows how we define multiplication. It's going to be very helpful when we talk about multiplying matrices together too. But it's really maybe not the most efficient way to do it. It makes sense by its definition, but it really isn't going to give us the fastest way to think about it. And it's something that we're not going to really want to do later on. So let's take a look at doing this another way. Let's get a new color. Hope you like neon blue. And let me actually go ahead and rewrite these matrices. Well, the matrix and the vector, I should say. I can think of this vector as a matrix with 2 rows and 1 column, but we'll just call it a vector. So what I want to do, and I think what's helpful with this, and we're going to be doing this eventually anyways, so let's go ahead and just get it out of the way, is thinking about sizes for multiplying matrices. Now this first matrix, we always go m by n, meaning row and then column. I have 1, 2, 3 rows by 2 columns, so it's a 3 by 2. And then this other, think of it like a matrix, has 2 rows by 1 column. Now important for multiplying matrices together in general, for this first matrix, the one on the left, I need to make sure that the number of columns matches up with the number of rows for that next matrix on the right. So really I'm looking here towards the inside. They're both 2's, so they match up. Since they both match up, the size of the product is going to be these outer values. So a 3 by 2 times a 2 by 1, since the 2's match up in the middle, the result is going to give me a 3 by 1, those values coming from the outside. So that means I'm going to have 3 rows and 1 column. So I can go ahead and sort of get an idea as to how this is going to look. But I'm not going to close this because there's actually going to be some computations I have to do. What I want to do for the row vector rule for computing is I want to start by fixing this first row of my matrix A, and I want to multiply into the column vector, and I want to multiply corresponding entries and add them. So I get 1 times -2, the first entry is 1 times -2, which gives me -2, and then plus second entry is 2 times 3, which gives me 6. And I want to continue this process. So now for the second entry of A times X, I want to go to the second row of matrix A and multiply back through the column. And I'm multiplying corresponding entries and I'm adding. So first entry is -3 times -2 gives me +6, plus second entry is 1 times 3 gives me 3. And now I'm ready for that last entry. So now I go back to A and I want to go to the third row. And I want to multiply into that column vector. So first entry is first, that's 1 times -2 gives me -2, plus 6, so second entry is now 6 times 3. The second entry of the row, the second entry of the column vector, 6 times 3 gives me 18. And this is no different. We can see it's going to give us the same result. Of course, I don't want to get a different answer. It should be the same answer that I'm getting just two different ways. -2 plus 6 gives me 4, 6 and 3 give me 9, 18 minus 2 gives me 16. So it's just another way to think of it. And it maybe seems like it's taking a bit longer to go through and explain the process, explaining the mechanics, but once we get multiplying things later on in the course, it's going to be much faster to do things that second way. But we're here to get some practice in, so let's do the same for this next example. I'll use the space up above, of course. But what I want to do is I want to take the first entry of the vector, which is a 1, and I want to use that as a scalar weight to this first column of the matrix A, which is 1, 3. I'm going to add to this. Now I want to take the second entry of my vector, which is a 2, use that as a coefficient on the second column of my matrix A, which had entries 3, 2. And then lastly, so I'm adding to this, now I want to take the last entry of my vector, which is a 1, and multiply to the last column of my matrix, which has entries -4, 1. Now I can go ahead and I can bring these weights in. So multiplying by 1 doesn't really do much. I get 1, 3. Multiplying by 2 doubles everything, so that gives me 6, 4. Multiplying by 1, again, just going to give me the same thing back, -4, 1. Now I can add corresponding entries. So I'll say, okay, 6 minus 4 is going to give me 2, and then 2 plus 1 is going to give me 3. Just add them all up. You can go left to right, or I kind of jumped around. And then here I have 3 and 4 and 1. So I'd say, okay, 3 and 1 is 4, and 4 gives me 8. So I get the vector 3, 8. But there's another way that I can do this. There is another. And that's where I want to use this row vector rule, which eventually we're going to come to know as the row column rule when we start talking about matrices being multiplied. Again, I think it's good to start by talking about the sizes here. This has 2 rows and 3 columns, so it's a 2 by 3. And I'm multiplying to this a vector with 3 rows and just 1 column, so 3 by 1. So the result, if I can't sort of cheat and see it over there, since the 3 matches up in the middle, the result is going to be a 2 by 1. And I'll say, well, okay, so now I get an idea how it's going to look. There's going to be 2 entries, and it's just going to be a vector. But if I go through and think about that row column rule, we would say, well, first go to the first row of the matrix A and fix it and multiply it into the vector, but multiply corresponding entries. So the first entries, 1 times 1 gives me 1, plus the second entries are 3 and 2. So the second entry is 3 times 2 gives me 6. And then the third entries, -4 and 1, when I multiply -4 times 1 gives me -4. And then I can continue this process. Now I go down to the second row of matrix A and back through the entries of the column. First entries, 3 times 1 gives me 3. Second entries, 2 times 2 gives me 4. And then last entries, third entries, 1 times 1 gives me 1. And say, okay, so now I just want to add these things. So again, 6 and 1 is 7. 7 minus 4 gives me 3. 3 and 4 is 7. 7 plus 1 gives me 8. So I get that same vector, just another way to compute it. And let me know in the comments below, what do you prefer? Do you like this vector decomposition? Do you like this row vector rule that we just did in the blue? What do you think is best? Let's take a look at another example. So here what I'd like to do is I'd like to use the definition of A times X to write this matrix equation as a vector equation. Or we'll do vice versa for an example that is set up the other way. But in this case, I have, AX equals B is really what this is. A times X equals B. And I really want to think about this left-hand side, A times X, and decomposing it like we said before. So we said we would start with the vector X, and I would pick these entries out as scalar weights. So I would take this first value, 6, and I would multiply that into this first column. So that's 7, 4, 10, -3. And I would add to this, now I would take the second entry of the vector, which is a 4, and multiply that into the second column, which was 1, -2, 5, 5. And then this should be the same way of writing what I have on the left, and this should still be equal to this vector that I have with entries 46, 16, 80, and 2. So just another way of writing this. So I took the matrix equation that I was given, and now I have it written as a vector equation. This is our vector equation. Well, let's do the opposite for the following here. So now here I'm actually starting with the vector equation, and I want the matrix equation. And if you remember what roles these are playing, here I have the scalar weights on each of the columns. And these scalar weights are going to be a vector that I multiply by. So I can actually start there by saying, okay, so I'm going to have a vector for X. Maybe it might be better to even call the vector Z, ha ha ha, if you get my joke. Because the entries of that vector are going to be Z sub 1, Z sub 2, Z sub 3, and Z sub 4. Right, those are where I'm getting those scalar weights from, so that would go back into the vector. But that vector should be multiplying by, on the right of, a matrix. So here's where my matrix should be. And to build my matrix back, I just want to remember these columns that I have, these column vectors, should be the columns of the matrix. So that first column, if I assemble it back, should be 2, -4. The second column should be -1, 5. the third column should be negative 4, 3, and the fourth column should be 0, 2. So here I have another way of writing, ax is really this left-hand side, and then equals b is still the same. It's still just 512. So that's still the same. Let's take a look at doing sort of both. So here I have a system given. I have a system with two variables, x1 and x2. It says first write this as a vector equation, and then as a matrix equation. Now to write as a vector equation isn't hopefully too bad. We can sort of see that, and if I sort of even just do it visually, I can see all of the values that are being multiplied by x sub 1, and then all the values multiplied by x sub 2. So I have this system here, 4x1 minus x2 equals 8, 5x1 plus 3x2 equals 2, 3x1 minus x2 equals 1. And I can really get that vector equation even just from the aesthetics of it. We think, well, I have x sub 1 as a weight, and x sub 1 is being multiplied to what values? Well, I can just line them up here vertically, right? X sub 1 is being multiplied by 4 for the first entry, and then x sub 1 is multiplied by that 5, and then lastly by that 3. So far so good. And then I can say, well, what about that next weight? That next weight is x sub 2, right? Here I'm sort of looking visually, thinking sort of vertically as well. Next I have x sub 2 times a vector, and what is x sub 2 multiplying into? Well, it's kind of tricky to see, but it's really a negative 1 there, that minus sign, so negative 1. And here we have positive 3, and then another negative 1 for that minus x2. And then equals on the other side should be a vector 8, 2, 1. You say, okay, so I got my vector equation. Hopefully it makes sense where this comes from. And if I go through and actually do the vector arithmetic, you could, spend some more time decomposing this to really show what's happening behind the scenes. But I think it's perfectly reasonable to just appreciate the aesthetics of how this is lined up and build it from that. But I certainly can build back that system if I want to, bring in the scalar weights and then set them equal. But now from here, it brings me a great opportunity to build that matrix equation. So how am I going to build the matrix equation? Well, these column vectors I have should be the columns of my matrix. So that first column should be 4, 5, 3. That second column should be negative 1, 3, negative 1. And they should multiply by a vector. Here my vector should have these weights as entries in order. So respectively, x sub 1 and then x sub 2. And then this should be equal to that other side, right? Should be equal to that vector with entries 8, 2, 1. Bam. Got it. We're doing it. We're doing it. You're doing it. And I got all the space here because it was not so bad. So we'll jot a little note down here. Not so bad. Smiley face. That's how we look when it's not so bad. Let's take a look at a little bit more. So now we want to write the augmented system, the augmented matrix for the linear system that corresponds to the matrix equation ax equals b. And then solve the system and write the solution that we get as a vector. So right away, I'm going to remind what we sort of said at the beginning. If I want to talk about this system ax equals b, it's really just the augmented matrix where I have matrix A and then augmented with vector b. So what I can do right away is I can take this matrix A. So let me just rewrite it. A lot of rewriting in linear algebra, but not too bad. And then I'm just going to take that matrix A. I haven't sort of closed it yet because I want to augment with the vector 1, 2, minus 3. And now I can start that process of row reduction. I want to go through our elementary row operations to reduce this. And I can use that 1 in the upper left corner to get zeros directly underneath it. So that's going to be a good amount of row replacement. I'm going to work in row 2, replacing row 2 with row 2 plus 3 times row 1. And then I'm also going to want to, either in the next step or in this current step, I'm just going to do it right now to sort of save on space and time. I'm going to do something similar in row 3. I want 5 minus 5 to get that 0. So I'm going to replace row 3 with row 3 minus 5 times row 1. So I can rewrite row 1 to start. Just rewriting it. And then for row 2, I'm replacing it with row 2 plus 3 times row 1. So negative 3 plus 3 times 1 gives me that 0 that I wanted. Then I have to do the rest for the other elements, right? So negative 4 plus 3 times 2, negative 4 plus 6 is going to give me 2. And then 2 plus 3 times negative 1, that's 2 minus 3 is going to give me negative 1. And then 2 plus 3 times 1, so that's going to give me 2 plus 3 is going to give me 5. And then I can do my row replacement in row 3 as well, replacing row 3 with row 3 minus 5 times row 1. So I get 5 minus 5 times 1 gives me the 0 that I wanted. 2 minus 5 times 2, that's 2 minus 10, gives me negative 8. And then 3 minus 5 times negative 1, so okay, so that flips the sign. Be careful with those minus signs. That's going to give me 3 plus 5, gives me positive 8. And then negative 3 minus 5 times 1, negative 3 minus 5 gives me negative 8. And this looks really good so far. I can go ahead and clean this up a bit. So for example, here working in row 3, I can do some scaling. So here I could go ahead and scale this. I could divide everything by a negative 1/8. So we'll do negative 1/8 row 3. But while I'm at it, I might as well do an operation either now or in the very next step on row 1. I'm going to replace row 1 with row 1 minus row 2. And that's to help me try to eliminate some of these entries. I'm already starting to think about how my pivots, I'm hoping that my pivots fall nice and diagonal. So I'm hoping that I can get maybe a 0 where this 2 is in row 1. But let's see if I can do that. So here, if I replace row 1 with row 1 minus row 2, I get 1 minus 0 keeps my 1, so safe and sound. 2 minus 2 is the operation I needed to get that 0 that I wanted. And then negative 1 minus negative 1 is going to give me a 0 as well. So like a bonus 0, which is great. And then I have to work in the augmented element as well. So 1 minus 5 is going to give me negative 4. And I can go ahead and take a look at the rest. Now, I was using row 2 to do this, so I'm not changing row 2. So I'm rewriting that if I haven't already. But then in row 3, I said I was going to scale this, just to sort of do that as well. I'm going to divide everything by an 8 and flip the sign. So that's going to give me 0. It's going to give me positive 1, negative 1, augmented with positive 1. So it looks good so far, and I'm starting to sort of build my solution. Now what I can do is I can go ahead and try to work a bit further. Now, depending on what you want to do, you could do a row interchange, or you could do some extra scaling. Doesn't really make a difference. Let me just do a scaling. You could do a row interchange. So here where I divided everything by a negative 8, that's good. But if I want to now, I can actually scale this by a 2 to get some cleaner arithmetic. Love clean arithmetic. Let me know in the comment section below if you love clean arithmetic because you hate arithmetic. Let me know if you would do the row interchange instead. I'm thinking about it too. I'm thinking about it all day. But now what I can do is I can work in row 3 a little bit nicer. Nothing too crazy here, and just replace row 3 with row 3 minus row 2. And especially at the beginning of our course, sometimes it's nice to just go a little bit easier with the row reduction. Get everything where it needs to be. See this matrix? We're going to put a happy cloud in there. I'm just kidding. Let's do row 3 minus row 2 in row 3's position. 0 minus 0 keeps my 0. 2 minus 2 gives me that 0 that I wanted. Negative 2 minus negative 1, so that's negative 2 plus 1 gives me negative 1. And then augmented with 2 minus 5 gives me negative 3. So it's starting to look really good so far. Now I can scale row 3. And I just want to flip the sign, so we'll just replace with a negative 1 times row 3. Let me rewrite the rest, since that's not going to change yet. Row 1 looks great. But here, row 3 is going to be 0, 0, 1, augmented with 3. I just flip the sign. And now I can do some row replacement in row 2. So I can see my pivot. So first column looks good. Second column, I kind of want to scale, but I'm not going to scale yet. I'll leave that till the end. And then here, this third column, I'm really looking at, I want to get the 0 here where this negative 1 is. I can replace row 2 with row 2 plus row 3. So here I have my first row. I'm rewriting it. Doing the operation in row 2's position, I get 0 plus 0 gives me 0. 2 plus 0 gives me 2. Negative 1 plus 1 gives me 0. And then 5 plus 3 gives me 8. And then I can go ahead and rewrite row 3. And I'm almost done. Now all I have to do really is scale row 2. We said we don't want that to be a leading 2, it should be a leading 1, so I want 1/2 row 2. And rewriting, I have 1, 0, 0 augmented with -4. Scaling, I get 0, 1, 0 augmented with 4, right, dividing everything by 2. And then rewriting that last row, 0, 0, 1 augmented with 3. So now I can see my separate pieces of my solution. This is fully reduced. The coefficient matrix is fully reduced. I can see x sub 1 equals -4. I can see x sub 2 equals +4. I can see x sub 3 equals 3. But I was told to write my solution as a vector at the very beginning. And doing this isn't going to be crazy. It's not groundbreaking. I can call my vector x. Remember, we're solving ax equals b. So we solved for what vector x is. But x is going to be this vector with the entries x1, x2, and x3 in it. So as soon as I get my pieces to my answer, just put them in a vector. Just put them in a vector. Just put them in a vector. So I get -4, 4, 3. And that's my solution written as a vector. Nothing really too crazy about it, but that's how we want to assemble our solution. That's going to be helpful for later on in the course as well. Let's take a look at the following example. So here I have matrix A with rows 3, -1, -9, 3, and a vector B that's very nondescript, just with entries b sub 1 and b sub 2. I want to show that ax equals b does not have a solution for all possible vectors b. But I do want to then go ahead and describe the set of all b for which ax equals b does have a solution. So I'll say, okay, well, let's see how this is going to look. I want to start just the way that I did before. Take matrix A and augment with vector b. So rewrite matrix A as a coefficient matrix now, and augment with vector b. And then I want to go through some row reduction. And you can get crazy, fancy with your row reduction. I'm just going to go ahead and maybe scale row 1 up. So I'll do 3 times row 1. So then here, what's row 1 going to look like? Well, it's going to look like 9, -3, augmented with 3 times b sub 1. Just multiplying everything by 3. And I can rewrite row 2 the way it is. And now I'm going to do some row replacement. So I'm going to work in row 2 and replace row 2 with row 2 plus row 1. So let me rewrite row 1. Row 2, I'm going to get -9 plus 9 gives me 0, 3 plus -3 gives me 0, and here I'm going to get b sub 2 plus 3b sub 1 in the augmented entry. Right? I got to add them, so that's what it looks like when I add them. But now, and I could, scale back down row 1, I could go crazy scaling everything. But right now, I can actually see what a potential issue could be. This second row, if I think about what it says, when I write everything out, it would say 0 times x sub 1 plus 0 times x sub 2 is equal to b sub 2 plus 3 times b sub 1. Okay, well 0 times x sub 1 and 0 times x sub 2 is just 0, and 0 plus 0 is 0. So this is really saying that 0 would be equal to b sub 2 plus 3 times b sub 1. And this isn't going to work for just any value, right? If b sub 2 is 1 and b sub 1 is 7, it's not going to work. Right? If b sub 1 is 15 and b sub 2 is square root of 3, it's not going to work. Right? So there's a lot of different vectors with entries b sub 1 and b sub 2 that aren't going to work. But in fact, I have a relationship here that's going to tell me what will work. So this right here is the restriction for that vector b. And if I want to, I could actually solve. And here, I think the tendency would want to be to solve for b sub 1, but it's not actually the cleanest to do that. So I'd say, let's not really focus on standard convention then. Let me solve for b sub 2. So b sub 2 would have to be equal to, swing that over, a -3 times b sub 1. And these are the vectors b that are going to work. So I'm saying the vector b with entries b sub 1 is the first entry, b sub 2 is the second entry. It's only going to work if b sub 2 is -3 times b sub 1. I need that relationship, or else I'm going to get something inconsistent. I'm going to get 0 equals not 0, which is false. So you see, not everything's going to work, but as long as it follows this restriction, then hey, it's going to work. We'll take a look at a theorem. We'll see a couple examples of it, and then hey, we're out of here. Let's take a look at this theorem. Let A be an m by n matrix. The following statements are logically equivalent, which means If one of them is true, they're all true. If one of them is false, they're all false. So logically equivalent. So that means either all the statements are true or all the statements are false. And here we have 4 statements that are logically equivalent. Now for this, and we'll talk about this later, but this is really talking about just a coefficient matrix, not an augmented matrix. So the first statement says, for each b in Rm, the equation ax equals b has a solution. So that's the first one. Second says, each b in Rm is a linear combination of the columns of matrix A. The third statement says the columns of matrix A span Rm. And then the fourth comment here is that A has a pivot position in every row. And as we said, this theorem is only talking about a coefficient matrix, not an augmented matrix. Right? If an augmented matrix has a pivot position in every row, then the equation ax equals b may or may not be consistent. But now we have this follow-up question. It says, consider the following matrix, and here, we're all looking at it. Can each vector in R4 be written as a linear combination of the columns of matrix A, and do the columns of A span R4? And if I look back at these comments here, my logically equivalent statements, well, these are a couple of them, right? Can each vector in R4 be written as a linear combination of the columns of A? That's the second statement. Do the columns of A span R4? That's the third statement. I want to know, are these things true? Well, I want to use the fact that I can prove one of these things as true, and then I know that all of them are true. And if I actually sort of judge these statements, one of them is going to be much easier to work with than the others. In fact, a lot of these are very theoretical. But one of them talks about pivot positions. So actually statement D is going to be the easiest one for us to show. I want to row reduce. I want to know, is there a pivot position in every row? If I have a pivot position in every row, then it's true and all the rest are true. If I don't, then I know that statement is false. Since they're logically equivalent, all the other statements have to be false. So that's the idea, at least. So I want to work with statement D. I want to row reduce here. Let's see what we get. Let me use this. You never know what kind of space you're going to need, so I'm going to use all this usable space here. Let's start row reducing. So now I can use this 1 in the upper left corner of row 1 to try to get zeros underneath it. So let me actually rewrite row 1. And in row 2, I'm going to replace row 2 with row 2 plus row 1. So how's it going to look? Negative 1 plus 1 is going to give me 0. Negative 1 plus 3 is going to give me 2. Negative 1 plus 0 is going to give me negative 1. 1 plus 3 is going to give me 4. I'm going to go ahead and just rewrite row 3. Deal with it later a bit more. But also working in row 4, I can do some row replacement there as well. I want to get a 0 here if I can. I can use that 1 in the upper left corner. And I can do 2 minus 2 times 1. So I'm going to replace row 4 with row 4 minus 2 times row 1. And we'll get 2 minus 2 times 1 gives me that 0 that I wanted. I got to do the rest though. 0 minus 2 times 3, that's 0 minus 6, gives me negative 6. 3 minus 2 times 0 gives me 3. And negative 1 minus 2 times 3, that's negative 1 minus 6, is going to give me negative 7. And this looks really good. Now I would want to think about, for example, scaling, and I can scale row 3. So rewrite row 1, rewrite row 2. Row 3, I'm going to divide everything by a negative 1/2, so we'll do negative 1/2 row 3. So flipping the sign and cutting in half, so I get 0, I get positive 2, negative 1, positive 4. Does that look familiar? I'm just going to rewrite row 4. And now I notice that rows 2 and 3 are identical. So I can actually do some more row replacement. Well, yeah, I can do some more row replacement. I can eliminate a row is what I'm trying to say. Is I can work in row 3 and replace row 3 with row 3 minus row 2. And let me rewrite rows 1 and 2. Just get that out of the way. Row 3, 0 minus 0 is 0, 2 minus 2 is 0, negative 1 minus negative 1 is 0, 4 minus 4 is 0. You knew it was going to happen. I can rewrite row 4. And now, I'm not really going to go for a fully row-reduced version of this. Of course, we know that a row of all zeros should be at the bottom. So if you do want to do that courtesy, then you could just exchange rows 3 and row 4. but I'm not trying to get a full reduction here. I'm trying to answer a question, and it looks like I can already answer that question. So then we're just going to answer the question, right? My row of all zeros at the bottom. So that makes me feel a little better. But now I can say right away, hey, I'm not going to be able to get a pivot position in every row. How do I know that? I have a row of all zeros. There's not going to be a pivot position in that row since everything is eliminated. A row of all zeros, no pivot position. So we'll say since we don't have a pivot position in every row, then we can answer these questions. So we know that statement D is false, so all these other statements are false. So can the vector in R4 be written as a linear combination of the columns of matrix A above? Instead of rewriting this, because you know my handwriting isn't maybe the nicest looking, let me just answer it here. Say no. Do the columns of A span R4? I didn't mean to cross it out like that, but you know, I'm a little angry too, because the answer is no. Columns of A don't span R4. Can each vector in R4 be written as a linear combination of the columns of this matrix? No. Right, all these things fail because I was able to show that statement D is false. So then all of them are false. Let's take a look at another example, our last example for the section, and then I think this should be good. And we're going to use that logically equivalent statement again, that theorem that we had. Here I have three vectors, v sub 1, v sub 2, and v sub 3. And I want to know, does the set of vectors containing the vectors v sub 1, v sub 2, and v sub 3 span vector space R4? Now, why are we talking about R4? Each of my vectors has 4 entries. So these vectors are working and operating in vector space R4. So what do I want to do? Well, to answer this question, I want to do what I did before. I want to talk about pivot positions. And so to do that effectively, I want to build a matrix. And I want to take these vectors as columns to build my matrix. So my first column is going to be 1, 0, negative 1, 0. My second column is going to be 0, negative 1, 0, 1. And my third column is going to be 1, 0, 0, negative 1. I want to know what's the deal with the pivots. Now I'm going to start by doing some row interchange. I'm going to kind of do this a bit sort of strategically. I'm going to go ahead and, well, let me put row 3 in row 1's position. So I'll swap then row 1 and row 3 seems the most honest way to do it. But you could really get crazy and just do a free-for-all and just move them all around. So row 1 is going to be this negative 1, 0, 0. Row 2, I'm not changing what that one is. Row 3 is going to be 1, 0, 1. LOL. And then row 4, I'm leaving that 1, 0, 1, negative 1. But now I'm going to do some scaling. So I'm going to flip the sign on row 1, my new row 1. So negative row 1. I'm going to flip the sign on row 2 as well, negative row 2. So row 1 is positive 1, 0, 0. Row 2 is 0, positive 1, 0. And rows 3 and 4, I'm going to leave them 1, 0, 1, 0, 1, negative 1. But now I can really do some pretty heavy row reduction. So here I can use this 1 in the upper left corner to get zeros underneath it. So that means I can work in row 3, replacing row 3 with row 3 minus row 1. So let me rewrite row 1 and row 2. And then row 3, I'm going to get 1 minus 1 gives me 0. 0 minus 0 gives me 0. And then 1 minus 0 gives me 1. And then if I want to, I can do some more work as well. I could work, for example, in row 4, replacing row 4 with row 4 minus row 2. Seems reasonable. 0 minus 0, sort of jumping over, gives me 0. 1 minus 1 gives me 0. Negative 1 minus 0 gives me negative 1. And then I can work just one step further, right? I can replace row 4 again with row 4 plus row 3. So rewriting rows 1, 2, and 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. In row 4, I'm going to get 0 plus 0 gives me 0, and then again, but negative 1 plus 1 gives me 0. Now we have our answer. So we'd say, well, look, I have a row of all zeros at the bottom. So I have a row of all zeros at the bottom, which means I don't have a pivot position in every row. So I do not have a pivot position in every row, which means that the set of vectors v sub 1, v sub 2, and v sub 3 do not span R4. Right, because I'd say the columns of the original matrix, really I'm saying the columns of matrix A, this was my matrix A, the columns of matrix A don't span R4, and those columns happen to be the vectors v1, v2, v3, so the set of vectors with v1, v2, v3 don't span R4, so the answer is no. Now, if you've seen more linear algebra, or if you've sort of been familiar with some of this material, there are some comments that I can make right away. I don't want to say too much and give it away, but if you're thinking of something, let me know in the comment section below. But if you're getting a little bit frustrated by what happened here, because I do have a nice sort of diagonal entries of ones, right? There's no way I can really get pivots in every single row, considering I'm sort of limited by the size of the matrix, right? I can get pivot here, I can get a pivot here, but then where's the other pivot going to be? Someone's going to be left out. What I do have, and this isn't really what we're going to talk about in the course yet, but we are going to talk about it later, what I do have is a three-dimensional subspace of R4. We haven't talked about that stuff yet. We are going to talk about that stuff. This is just if you're getting ready to hit that thumbs down button, let me just sort of clear it up for you. So we're going to say it doesn't span R4 by what our theorem says. It gives us some subspace, though, which is worth mentioning. We're going to talk about that later on in the course, definitely. But for now, we have our answer. I'm feeling good. I hope you're still feeling good. I hope you're feeling great. But hey, that's going to be it. So we are all set. You know, no matter where you are and what you're doing, I want you to always remember to keep learning, keep dreaming, and to follow your heart. And you know what? We're going to be back at it with more math. But until then, I will see you next time. And hey, take care.